the subtraction of the Raman response by Z1 at close to room temperature 280 K. So when we decrease temperature, we see a dip and a fan. And we're above TC. And this dip and the fan, which corresponds to a transfer of spectral weight, is not due to superconductivity because it appears above TC. And now to show you the effect of superconductivity, please look at the left panel. When we enter into the superconducting state, we have a hand here which grows up at low energy, which grows up here, as you can see here, the blue line, and it grows up again, and that is the nodal superconducting. So at the end, at low temperature, we see both the nodal superconducting gap and the amp of the charge density wave. So we are confident that it's a charge density wave for many reasons. So the first one is that if we compare our results, deep and amp in Mercury 1, 2, 3, it's very similar to what we get from the well-known erbium 3 telluride, which takes charge density wave order, and this deep and the amp, this is the blue curve here, deep and the amp disappears above the transition temperature of the charge density wave, which is about 287 K. This is the red curve. So we have exactly the same structure. The second reason is looking at the transition temperature of the charge density wave. So we can define the transition temperature of the charge density wave by measuring the integrated area of the amp and look at its collapse. When this integrated area collapse, we can define the transition temperature of the charge density wave. So we do that for several doping, for strongly underdoped system with a critical temperature of 105 Kelvin. This is a Mercury 1, 2, 3. And for an underdoped sample, a slightly underdoped sample, and finally for an optimal dope sample. And we measure at each time the integrated area of the peak as a function of temperature to find where it collapses to define the transition temperature of the charge density wave. So we can see that it's non-monotonic, and this is reported here. It is non-monotonic, and it's exactly what we get in YBCO or in Mercury 12001 from X-ray diffraction on NMR measurements, where they find that the transition temperature of the charge density wave as function of doping is non-monotonic. But here is a sample which has not yet measured by NMR or X-ray diffraction. So the idea is to take exactly the same sample as the sample which has been already measured by X-ray diffraction. So we get the Mercury 1201 and we detect the amp. We take the YBCO and we detect the amp also. And then as a function of temperature, we can determine the integrated area of this amp and define the collapse of the integrated area to define the transition temperature of the charge density wave. So we find 200 K for this compound, for this specific doping, and here we find 140. So now if we report our Raman data, the red spot on the phase diagram get from the X-ray diffraction and NMR diffraction, we see that it fits pretty well with the transition temperature found by the other spectroscopy technique. Here we have performed a measurement on YBCO of two different doping levels. This is two spots here, and it also fits pretty well with the transition temperature of the charge density wave got from both NMR and X-ray diffraction, which make us confident about the nature of this amp that we find in Raman spectroscopy to be the charge density wave signal. So now we can go further, and by looking at the maximum of the energy of this peak, we can determine the energy of the charge density wave. So we define the energy scale of the charge density wave at the top.
Alain, you have 3 minutes.
Okay.
Is it okay?
Yes, okay, thank you. So, this is the energy of the charge density wave here. And of course, we can see it more clearly if we make the subtraction between the Raman spectra at the lowest temperature and the Raman spectra just at the transition temperature of the charge density wave. So here we get this maximum. We see that it decreases in energy, but we are a little bit bothered here by the signal of the superconducting gap, as you can see. So the idea is to make the measurement just below TC, but still in the superconducting state to benefit of the long quasi-particle life. So if we do that, we can see I reduce considerably here. I reduce considerably the signal of the superconducting gap, and I can emphasize the signal of the energy of the charge density wave. So now we can plot, this is a good triangle, we can plot the energy of the charge density wave, and it's very close to the energy of the antinodal superconducting gap. And these three energies decrease linearly as function of doping and follow T star, and not follow TC. The only one we follow TC is the nodal superconducting gap. So let me summarize. The energy of the charge density wave is proportional to the energy of the antinodal superconducting gap, and it's proportional to the pseudo gap and follow T star, while the energy of the charge density wave is no more proportional to the transition temperature of the charge density wave and no more proportional to TC. Sorry?
Summarize, yeah.
Just to summarize, the energy of charge density wave decreases linearly as function of doping with non-monotony, exactly as the antinodal superconducting gap is decreased linearly, and the does not follow TC. So these two orders are non-conventional in nature and then cannot be decreased by a loop theory because they are not proportional to the transition temperature. And the last point is that the energy of the charge density wave is very close to the energy of the antinodal superconducting gap. They are proportional to the pseudo gap and follow T star. So the scale of the antinodal superconducting gap and the charge density wave gap are intimately connected and related to the pseudo gap. This allows us to make the following conjecture, is that the pseudo gap phase will be a kind of primary order which controls both the antinodal superconducting order and the charge order. And this paves the way for new theoretical approaches for understanding the pseudo gap phase, such as the fractionalized charge density wave proposed by Pepin, and there is also other proposals by Patrick Lee about Ampere and Perrin, etc. And all these theories have a common point. They propose that there is a net momentum for Cooper curve which allows to combine superconducting order and the charge density wave. And this is in agreement with our experiment. Thank you for your attention, and sorry for the delay.
No, it's okay. Thank you very much.
Questions? Questions from the hall? No question?
No, wait a second.
Let's see the question from online question.
Online, I don't see any question. So let me ask a question to Alain. just for the discussion. So Alain, this is a fantastic set of data, and what it tells is basically like charge density wave is not an epiphenomenon, but it's kind of phenomenon of magnitude comparable to spare conductivity. Would you agree with this? And how would you explain then that other probes had so much problem, I mean, put so much time to observe it?
Oh, okay.
Like X-rays or, you know, it took very long. Even for you, actually, with Roman, it took long to... Is it hidden in a sense or something like that?
Oh, there is the point is that, as mentioned previously, when we have to find the good way to detect the charge density wave and especially the energy of the charge density wave, because the effect of the pseudo-gap is huge and destroy all the quasi-particles along the principal axis of the movement. So if you want to detect the charge density wave, you have to go a little bit away from the antinodal region. This is the reason why we are looking in the nodal region to detect it. And the other point is that Raman spectroscopy is an energy probe. It is not a momentum resolve probe. So if you want to try to detect the charge density wave with a momentum resolve probe, is not easy for the charge density wave because this charge density wave has a very short range or length. So we need to use an energy probe to detect it. And this is the case of the Raman spectroscopy. This is one of the reasons why it's difficult from angular result photoemission spectroscopy, which is a momentum probe, a momentum resolve probe to detect easily this charge density wave.
Okay. No questions? No questions third time? Let's thank to the speaker again. And our second speaker, Catherine Pepin, will give a lecture on fractionalized pair density wave and underdoped cuprate superconductors. Всъщност няма... Чекай.
Okay.
Okay, so it will be short.
Así lo vive.
Or I can take these 15 minutes and we go to coffee break. At least I am one of the chairpersons, so except if Todor is pushing me out, I can do whatever I want. So, okay, so I would like to first thank Alain for the wonderful presentation of what I will present you now. I will try to make it short, but it's the idea of, I did a presentation a few days ago with an introduction to cuprate superconductors. Yeah, okay. Good, good. Okay, here is better. Nah, man. Okay. So I did a presentation a few days ago about cuprate superconductors. And here it will be more detailed of what we did with this idea of fractionalized per density wave. It was indeed extremely inspired by the data Alain just presented on Raman scattering. This was one of the main inspirations for this idea. So I don't go over the diagram. First, I don't have time, and you heard that already in a previous talk. I will present just the idea of fractionalization. So when you fractionalize an electron, as here, you cut it into a charge holon and a spin-on, and this is operator or field space. And in order to control the number of states on site, you impose a constraint which says that the number of spin-ons and holons is equal to 1 at every site. And this is accompanied by an emergent gauge field, so a gauge transformation with a fictitious U1 gauge field here. And the system, you can see, if you put the gauge field, is invariant with this transformation. So we decide to do the same, but for a boson. And a boson which is fragile, which is a per density wave boson. So here it's in terms of operator. Here is a per density wave. Write it as a commutator of charge modulation and a boson corresponding to pairing, so particle-particle and particle-hole modulated pairing. So now we have a constraint, again, between the two fields, and the per density wave fractionalized into a charge 2 bosons and an operator here, particle-hole, which breaks translational symmetry. Again, you have a U1 gauge theory, a gauge field, which is emergent here. And our on that is a pseudo gap is an entangled state of the two with a constraint. So the two orders we know are in competition. So it is our way to put them in competition, not by Gibbs-Borlado, but by entanglement. And it requires an emergence of a gauge field at T star, which is not such a simple structure if nature decides to do that. So we wanted to test this idea on experiments. Aha. Ah, good. Sorry, it's not working. No. Oops. Oh my God. You are doing something, no?
If you press it too many times, then always if you press it too many times, then it's perfect.
I'm back to...
There's a lag.
Okay. No.
The software is too lag.
I think we need your help.
Oops. Which slide were you
Okay, so this is the slide. Yeah, okay. So this is a slide. So the system below T star is described by Van effective field theory, which is a chiral rotor, a quantum rotor model. So it's a chiral model, which is equivalent when you do a Hopf mapping to a CP1. So it will be equivalent to a nonlinear sigma model with a gauge field. And we have some predictions already of what's going on here. So you have incoherent bosons at plenty of them in this region. Some emerging gauge field at T star. And at TC, importantly, all the phases are frozen. So this is very non-trivial if you do that, because the phase of the charge order parameter is frozen with the phase of the superconducting order parameter. This is something else. No, really, guys, really, I'm saying in front of everybody, this, like, you need to buy software which shows a PDF to. So we skipped one, I think. Okay, I think I will stop here. I'm really annoyed. I'm sorry, but it's just impossible. I don't know. Look, I think we will stop here this presentation. This is just not working. And let's go to next. Sorry about that.
Oh. Okay, my sympathy, because this was one of the topics which I came here in Bodrum to listen.
Ah oui, je vous raconterai. Non, mais là, c'est pas possible. Je pense que là, il faut bien qu'il y ait quelque chose qui va.
Okay, we have to the next lectures. Next lecturer is Anna Myasnikova. She will speak about two-component ground normal state and pseudo-gap in systems with strong electron-phonon interaction and cuprate-like dispersion.
Thank you very much. Family screen. I will family screen.
We are hearing you.
Thank you. Thank you.
Yes, you can start.
Thank you. Do you see my screen? Do you see my screen?
Yes, we are seeing your screen.
My screen?
Yes.
Can you see my screen? Can you see my screen? Oh, thank you.
Yes,
first of all, let me express my full gratitude to the conference organizing committee and to Professor Agent Sir for getting me the opportunity to take part in this excellent conference. I will tell about two-component ground normal state and pseudo-gap in systems with strong electron-phonon interaction and cuprate-like dispersion. There are several experimental signs of strong electron-phonon interaction in cuprates. The most known are the broad bands in angle resolved emission spectroscopy spectra and optical conductivity spectra, and giant phonon anomaly. Giant phonon anomaly is a softening of phonon modes with wave vectors near the Church-Jordan wave vector. And broad bands in optical and angle resolved emission spectra stem from the multiphonon generation at decay of the polarization potential well. It is convenient to describe such polarization potential well in terms of coherent states, the decomposition of such states in terms of the states with a certain number of quanta energy harmonic is Poissonian-like. There are two types of electron-hole interaction. At strong short range for whole-state electron-hole interaction, small bipolarons and polarons are formed, and they are described in works by Alexandrov and Mott. This type of bipolarons and polarons are small. Carriers are localized in one elementary cell, and they have negligible mobility. At strong long range of Röhrlich electron-hole interaction, large polarons and bipolarons are formed. They are much larger than the unit cell, and they can coherently move through the crystal lattice, and it is more important for the present consideration, they can coexist with delocalized carriers at high carrier density. Indeed, if we write uncertainty relation, then we can see that the bipolaron size, or bipolaron size, or polaron size is connected with the maximum momentum of the carrier in the bipolaron to polaron, and this formation of large bipolarons with the size much larger than the unit cell disturbs only the small part of the band of the first Brillouin zone, so the rest of the dispersion is can be filled by delocalized carriers. In such approach, naturally several characteristic features of cuprates naturally appear. For example, two-component carrier system comprising autolocalized and delocalized carriers result in a high energy anomaly and antinodal angle result photoemission spectrum, in pseudo-gap and nodal angle result photoemission spectrum, and scanning tunnel and microscopy spectrum. In different doping dependence of the charge ordering wave vector in various cuprates. The illustration of experimental results on this different doping dependence is represented here. And the temperature of the charge ordering onset is lower than the temperature of the pseudo-gap onset in such approach, and strong temperature and doping dependence of the whole constant appear. Display of coexisting bipolarons and delocalized carriers can be observed in model and result for the emission spectroscopy. High image anomaly, it is the vertical dispersion or waterfalls near some wave vector. Note that this wave vector coincides, approximately coincides with the charge ordering wave vector in cuprates. This high energy anomaly stems from different energetic cost of the system relaxation after photoemission from bipolaron state or delocalized state. The calculation we made uses the energy conservation equation and the coherent state basis for the polarization field in bipolarons. Here in the upper row, the results for electron dope system, it is our calculation. It is the experimental result from this paper. The bottom row represent results for whole doped, undoped, and whole doped systems. Calculation is the same work, and the experiments in these three works. The left panel shows our calculation, and the right panel in each of these figures represents the experimental. It is undoped compound, low whole doped, and high overdoped with holes sample. To consider ground normal state in systems with strong long-range electron interaction high carrier density, we use simple, well-known Fröhlich Hamiltonian and generalized variation method. In such case, the R capital denotes the position of the bipolaron centers, like shown like this. Then, if we extract the in this radius vectors of carriers, then we obtain for the average electron of the electron-phone interaction, it contains such sums. These sums, in similarity with well-known textbook in condensed matter physics results differ from zero only if the wave vector of the phonon harmonics of the phonon field coincides with some specific charge ordering wave vector, which is related with the period of this structure of the bipolar centers. And note that the expression for charge ordering wave vector coincides with the expression for the maximum momentum of the carrier in the polaron or bipolaron. Using this generalized variational method, we carry out variation over the bipolaron size, taking into account energy of localized and delocalized carriers. Delocalized carriers also, the energy depends on the bipolaron size through the maximum momentum in the bipolaron. And the results are represented here. They are all from this paper. Here is the curves represent the calculation results, and stars represent the experiments. Here is the experiment in electron-doped system. Here is the experimental data for plantanium system in Alaska. Here are the IPCO result and one of the BISCA results. It is the result for BISCA 2201. So we can see the remarkable consent with experimental data and different doping dependence. Why it is different? Because in the upper row we show the case where the bipolar interaction is neglected, and the lower row demonstrate the case with taking into account the bipolar interaction. The bipolar interaction can be more or less important depending on the static dielectric constant or the size, and so the distance between the bipolar centers. We also model the resonance elastic X-ray scattering on the bipolar charge ordering. We prepare the system in such a way using even wave function, and we consider cases with different filling of these positions. Here is the equilibrium positions, and here is the instantaneous positions if all positions are filled. We average our results over 20 instantaneous snapshots in each calculation, and we obtain that the bipolar charge ordering will be observable in RIX spectrum only if the more than 50% of positions are filled with bipolarons. Also, we can consider the cross-section of the peak, of the charge ordering peak, and we obtain such result. It is coincides with this result observed in experiments, but in this experimental work, it was interpreted as the display of stripes. But we obtain such form of the cross-section in checkerboard structure. Now let us come to the gap. To do this, we consider influence of the potential created by bipolar charge ordering on the delocalized carriers. The charge density in charge ordering can be described with the sum of cosines, as was shown here. So, if we know the charge of one bipolaron, it is how it is shown here. One can calculate the potential created by charge ordering of bipolarons. It will be like this, or when we take into account that near antinode, where the theta gap is formed, the one component of the momentum is much larger than the other, we can first consider this simplified potential, and then the more complex potential like this. To consider the one-dimensional, the more simplest potential, we divide the crystal into stripes, and for the two-dimensional into squares. In each square, we consider the potential of the charge ordering is constant. And we solve the Schrödinger equation with this additional charge ordering potential. considering the states with one and the same energy for all the stripes or squares, as we are looking for stationary state. Naturally, it is convenient to use decomposition of the wave function in terms of Bloch wave functions, and then we can simplify our equation by substituting instead of this part the Bloch carrier dispersion. And then we come to this equation, which determines the wave vectors, the momentums of the carrier in each stripe or square, depending on the boundary which this momentum crosses. So the most convenient way to solve this system of equations is to do it graphically. If we so we can model the Kupras dispersion, and we model it with such expression which catches the arc shapes of the Fermi surface and constant energy surfaces and the flat band near the Fermi surface near the antinode in this region. Using this dispersion, we calculate the momentum space trajectories of quasi-particles for one-dimensional and two-dimensional potential respectively. Here we show two different momentum space trajectories for the quasi-particles with the same energy, but with different momentum in the zero potential layers. The first quasi-particle, its momentum space trajectory can reach both the minimum and maximum kinetic energy. So the real solution of the system exists in all the stripes or squares, in all the stripes, and this is real quasi-particles. The second quasi-particle cannot reach the surface with the maximum kinetic energy. So in a lot of stripes, the real solution of the system does not exist, and such quasi-particle is forbidden in case of such hole-like dispersion. Close situation occurs in two-dimensional case. Here is this quasi-rectangles are momentum space trajectory, and if the Fermi surface angle is smaller than shown here, the quasi-particle also cannot exist. It is forbidden by the Kupras dispersion, hole-like dispersion. We can construct angular results for the emission spectroscopy spectra. If we catch the carrier photoelectron with the momentum near the antinode, we will see that it has not energy which corresponds to this momentum according to dispersion, but the energy which is lower by the amplitude of the charge ordering potential. To construct the spectrum, angular result for the emission spectroscopy spectrum, we take the cross-section of this momentum space trajectory for permitted quasi-particles and put them into corresponding place in this diagram. The intensity is calculated as inverse area of the momentum space trajectory. And we can see that the angular for the emission spectroscopy spectrum obtained demonstrate all the peculiarities characteristic of antinodal angular for the emission spectra in cuprates, namely the giant broadening and the so-called particle hole asymmetry. It is the mismatch between the Fermi momentum at high temperature, and the so-called backbending momentum, which is here. The same is observed in experimental spectrum from this article. This is the Fermi momentum at high temperature, and this is the so-called backbending point. If we choose the dispersion with the smaller Fermi momentum, the coincidence might be better. Our approach allows also to take into account inhomogeneity in, it is a previous slide with calculated weights of the pseudo gap as a potential, as the amplitude of charge ordering potential. It is shown with circles. And here the squares represent the experimental results in different systems. Here we represent the temperature of the charge ordering onset. It is calculated as the temperature.
You have 3 minutes.
Thank you. I will be in time. And here is the temperature of the charge ordering onset. It is calculated the temperature of thermal decay of 90% of bipolarons. We can know that temperature of the charge ordering onset is lower than the temperature of the pseudo gap onset because 50% of the bipolarons necessary to observe charge ordering are less than 90% of bipolarons necessary to observe the pseudo gap. And this approach allows also to take into account inhomogeneity in dopants ion distribution because they also create their potential, which should be added to the potential of the charge ordering, like this. And we have found that only if the size of inhomogeneity area is equal or larger than the period of charge ordering, then it influences the pseudo gap weights, and approximately the same grains with the charge of the order of the charge ordering period are observed experimentally. Now let us describe how we calculate the temperature of the bipolarons thermal decay. It is made with the distribution function published in this paper, distribution function for carriers which can be autoalkalized and delocalized. It is a special distribution function, and the density of bipolarons and delocalized carriers in this approach are described as a function of temperature. Approximately the temperature of decay of a half of bipolarons can be calculated using this expression where U is the maximum group velocity of phonons. Using this distribution function, we can estimate temperature and doping dependence of the Hall constant in cuprates. If we suppose that the holes from the upper half of the lower Hubbard band do not take part in conductivity and transport effects until the holes are localized in bipolarons, we obtain such expression for the number of holes and the expression for and the Hall constant in such case will be like this. And here is the experimental results from this article. Here we see some inconsistencies, so the additional suppositions should be made, maybe about percolative character, maybe something like that. This work is in progress, it is unpublished yet. Thank you very much for your attention.
Thank you. Let's take to the speaker. We have time for one or two fast questions. Question from the hall, yes?
Thank you for a very nice talk. Do you think your bipolaron picture could account for the results, for example, of Raman scattering that we just listened to? Or have you already thought about that? Or because it's a description of the charge system, which is very unique.
Thank you. It is a good question. I was interested in the previous talk about Raman scattering. Yes, some features are in very good consent with this experiment about the proportionality of the pseudo gap to the charge ordering gap. It is in line with our theory, of course. Maybe some moments are not considered in our theory, but we will consider them later, known the experimental results on Raman scheduling.
Is there also questions in the room? Or if you are online, you can ask questions in the chat.
No questions.
Another here.
Now, we are, let's say thanks to the speaker again. Now we are switching to our next lecturer, James Story. He will told us about towards a single model description of cuprates in pseudo-gap state.
Hello. Just
Okay, we are
showing. Hopefully you can
seeing.
see that.
Great.
Great.
So I'm James, and thank you for the introduction and for the invitation to talk to you today. If you could mute your microphone, that'd be good. So I'm coming to you today from my home in New Zealand. I'm sorry I couldn't attend. Our borders are still closed due to COVID. So today I'm going to present a brief review of some of the phenomenological models used to describe the pseudogap phase in underdoped cuprates, which dominates the underdoped region of the phase diagram and often shown to terminate just below 0.2 holes per copper. Obviously, we know now the phase diagram is more detailed. For example, there is a region of superconducting fluctuations just above the TC dome, and as a result, the superconducting gap will persist into this region, giving the appearance of a pseudogap. As talked about earlier, there's also a region of charge ordering near 1/8 doping, which becomes stabilized at high fields. I won't be talking about that today. I'll be talking about this pseudogap phase seemingly arising from some sort of coexisting order parameter. So the first evidence for the pseudogap came from these NMR measurements where a downturn is observed in the NMR night shift as doping is reduced, signifying a gap in the spin degrees of freedom. These later measurements on the right show that the downturn sets in just below 0.2 holes per copper in YBCO. I'm sure I don't need to tell anyone here, but to revise, obviously a superconductor is characterized by an energy gap that closes at TC. If we multiply the density of states by this thermal window function and integrate, we get the electronic entropy, which exhibits a change in slope at TC, and therefore we get a jump in the derivative at TC, which is the specific heat jump. Obviously in cuprates, the gap has a D-wave symmetry, so linear dependence about the Fermi energy, which gives rise to a linear temperature dependence in the specific heat. So here is John Lorem's classic data for YBCO. In the overdoped region, the specific heat jumps are nice and large. The underlying specific heat is relatively flat, and the entropies almost coincide. And this suggests that the density of states in this region is roughly independent of energy and doping. However, as we move into the underdoped region, the specific heat jump collapses, which we can plot on our phase diagram. There is a downturn like in the NMR in the normal state specific heat, and there is a persistent loss of entropy right up to the highest temperatures that we measure. So this suggests that the pseudogap itself is temperature independent. We can model these features by a second energy scale, the pseudogap energy, which obviously proceeds like so. Specific heat tells us that the pseudogap is fundamentally different to the superconducting gap, where the superconducting gap is states conserving, meaning that the in-gap states get transferred just above the gap edge into these coherence peaks. The specific heat and the loss of entropy suggests that the pseudogap is non-states conserving, meaning that we're transferring these states or spreading them out over a much wider energy range. John modeled this using a triangular cutout in the density of states shown by the dotted line, and this gives rise to a reduction in the specific heat jump, a smooth downturn, and a persistent loss of entropy, consistent with experiments. So specific heat, a bit like Raman, doesn't tell us about the momentum dependence. So for that, we need momentum resolve technique. This is what we expect the overdoped electronic structure to look like. And obviously the Fermi surface is that region separating occupied from unoccupied states, and is hole-like because it encloses the unoccupied states. In 1998, angle resolve photo emission showed us that the pseudogap opens near the zone boundaries at the so-called antinodal regions, leaving these ungapped regions of Fermi surface come to be known as Fermi arcs. Possible explanations for these arcs are that they are thermally broadened point nodes, or that they form one side of a closed pocket. So our triangular gap model evolved into a Fermi arc model where we can now specify the size of the Fermi arc using this angle parameter. And the finite Fermi arc gives rise to a residual density of states at the Fermi level. So our gap is no longer a complete gap, it's more of a depletion, hence the name pseudogap. Below TC, the superconducting gap opens up on these ungapped regions, giving rise to a kink in the gap structure, similar to what is seen in some of the tunneling work. Now, in this two-gap picture, the pseudogap removes states of the Fermi surface that would otherwise be available for superconductivity. As a result, the effective superconducting gap is reduced, and this leads to a weakening of superconducting properties such as the superfluid density. This two-gap picture does quite well at explaining Raman spectra, the work shown by the first presenter, and can explain the so-called nodal-antinodal dichotomy. So if we select a B1G polarization where we're probing around the antinodal region, what we find as doping reduces as the peak in the spectra shifts to higher wave numbers, as shown here, due to an increase in pseudogap magnitude. Whereas in the B2G polarization, where we're probing around this arc region, the peak in the spectra shifts to lower wave numbers due to a shrinking of the Fermi arc and a reduction in the effective superconducting gap magnitude. Now, the problem with the Fermi arc model is that a Fermi arc breaks the definition of a Fermi surface. It no longer encloses occupied or unoccupied states, and the discontinuities at the edges pose problems for calculating transport properties which depend on the derivative of the electronic structure. And so one way around that is to, of course, assume that the arc is one side of a pocket, leading us to these Fermi surface reconstruction models, of which two examples are shown here. So in these models, the large hole-like Fermi surface in the overdope region transforms into these small pockets near the nodes, and there is an intermediate region where we also have electron-like pockets near the antinodal region. These two models are quite similar, the main difference being that in the spin density wave reconstruction, we're simply folding the zone along the diagonal, and hence the pockets are symmetric along that diagonal line. And there is some limited photo emission data in support of both of these pictures. So this animation shows the reconstruction of the electronic structure as we switch the pseudogap on. I'll be largely focusing on the YRZ model, the resonating valence bond spin liquid model proposed by Yang, Rice, and Zhang. So in this model, the nodal hole-like pocket is caused from the lower branch here poking through the Fermi level, while those electron-like pockets near the antinodal region are caused by this upper branch starting to rise through the Fermi level. Some key features to note that in this picture, the pseudogap first appears entirely below the Fermi level. Also, as the electron-like pockets begin to disappear, the pseudogap then begins to span the Fermi level. Note too that, as mentioned by our last speaker, there's a particle-hole asymmetry in the pseudogap. And furthermore, this gap appears to be non-states conserving, so it has that property which would describe the specific heat also. The particle-hole asymmetry becomes relevant when we want to look at thermoelectric power measurements, because that observable is sensitive to asymmetry in the electrical conductivity about the Fermi level. So put simply, if our conductivity below the Fermi level is larger than the conductivity above the Fermi level, we'll get a positive thermopower, and vice versa. And the energy range that we add to our scales here depends on temperature. So if we calculate the thermopower from the YRZ model, remembering that at the onset of the pseudogap it appears below the Fermi level, this leads to an undulation or a down, up, down temperature dependence in the thermopower. There's a very subtle hint of it in the data points, and note that this corresponds to a very high doping near 0.25, and I'll come back to this point shortly. Another property that is sensitive to this sort of reconstruction is the Hall number. So the Hall number is a measure of the carrier density, and strictly speaking, for a circular Fermi surface is proportional to the area enclosed by the Fermi surface. So in overdoped cuprates, we have a large hole-like Fermi surface enclosing 1 plus P holes per copper. The 1 comes from the fact that the copper atoms are half filled and so have 1 hole associated with them. In the underdoped region, the smaller pockets are proportional to P holes per copper. If we calculate the Hall number from this Fermi surface reconstruction, we could see that the Hall number transitions from 1 plus P down to P, and it is accompanied by this transition region here, which corresponds to the dopings where the electron-like pockets are present. So in the same year I did this work, these nice high field measurements were done by Louis Teifer's group, and high field experiments are really proving to be a great way to expose underlying normal state behavior. And as you can see, they reported a very similar transition in the Hall number. If you overlay those data points, there's almost an exact match. And this to me is the best support yet that the pseudogap arises from some sort of reconstruction like this. But how else can we test this picture? So a feature of this sort of model is that it predicts a separation between the doping where Hall number changes and specific heat changes. So in this work, they showed, as I did, that at the onset of reconstruction, the Hall number decreases, whereas if you look at the specific heat jump at TC, that doesn't change to a lower doping. So they call the upper change P star and the lower doping here PE. And this corresponds to the region where the electron-like pockets start to vanish. So between 0.15 and 0.17. This becomes very interesting because of more recent work done by the team at Bristol, who report high field Hall number measurements for thallium-2201 and bismuth-2201. Note that the change in Hall number appears at a much higher doping than traditionally seen for the pseudogap around 0.2. And in bismuth-2201, it's particularly high, corresponding to the edge of the TC dome. We can, of course, model that in the YRZ model simply by changing the onset doping of the pseudogap, so that's very simple. And it's interesting to note, too, that, as I mentioned earlier in the thermopower, that this is where we predicted electron-like pockets, so there's a nice consistency there. It would obviously be good for thermopower measurements to be repeated on crystals. I think I've got 2 minutes or so. So let's just look at some other properties. Here is the superfluid density measured by μSR at 0 temperature. We could plot that on here. And also the specific heat jump for thallium-2201, which we can also overlay. Note that both properties will have to undergo some sort of maximum near a lower doping around about 0.18 or so, far below the onset of the change in Hall number. This change or decrease in superfluid density and specific heat is not expected in BCS theory and is believed to be due to an increase in pair breaking as we increase doping. If we add pair breaking to YRZ, it's possible, in fact, to push that maximum and specific heat jump down to lower dopings. Note that here is where we have the reconstruction occurring. If we increase pair breaking, our maximum and the specific heat jump can be pushed to lower doping, seemingly consistent with the experiment. I've talked about YRZ, but spin density wave reconstruction is a good candidate also. Obviously, the question is what could be driving this sort of reconstruction? The spin density wave reconstruction offers a nice symmetry with electron-doped cuprates, for which there is some evidence for that sort of reconstruction. Also, there was some nice ARPES results published on this 5-layer system where the innermost planes seem to exhibit a symmetric hole pocket consistent with spin density wave reconstruction. Running out of time here, but what determines P star? It seems to depend on the family of cuprate. Does it have a dependence on band structure parameters? And I'll skip this and go to my summary. So thermodynamics tell us there's a loss of states near the Fermi level. Spectroscopy tells us that it's an antinodal gap. And lastly, transport measurements tell us that this could be due to a Fermi surface reconstruction into small pockets. So thanks for your attention.
Thank you. Questions?
Yes, thank you, James, for this very nice talk. I have a question for you. With your reaction, if I understood, it's based on antiformagnetism and spin density wave. Can you explain the backbending? It's a bit technical, but from what you present, I think you will know exactly what I'm talking about. The backbending of the dispersion energy observed in Bismuth 2201. So according to Patrick Lee and others, you need some kind of particle symmetry, some kind of pairing in order to have this bending.
Yep.
Do you agree with that, and how do you account for it in your model?
Yep. So can you see this slide?
1 second. This one. So both models, Yang, Rice and Zhang, and the spin density wave reconstruction give you the separation from the Fermi wave vector due to this particle-hole asymmetric gap. So if that was what your question was about, it appears to be consistent with antinodal photoemission.
But to get the backbending on the right side here, you need particle hole, some kind of breaking of particle hole with particle. Do you
Yes,
agree with
so-
that? So
yes, I
effectively
agree with
your
that.
model also takes that into account.
Yes.
So you have some kind of preformed pairs hidden there.
Potentially,
I
yes.
don't
Yeah, superconductivity obviously occurs on top of this model, so yeah.
Okay, thank you.
May I ask a question?
Sure.
Excuse me, may I ask a question?
Yes?
Do you hear
Go
me?
ahead. Yes.
How do you explain your approach that in quantum oscillation measurements, the whole Fermi surface is not observed under doping? They see only Fermi pockets. Thank you.
Yes, so I have a slide there too, I think. Yeah, so a lot of quantum oscillations measurements are done near 1/8 doping in this charge-ordered region, and it's been suggested that there are electron-like, diamond-like pockets which would explain those measurements. It's possible that the high field is adding a further reconstruction of these small hole pockets into this diamond-like pocket. So that sort of evolution of the Fermi surface is how I understand things at the present stage.
And what about the volume of the electron pocket? Is it about 2 or 8% of the first Brillouin zone, or is it large?
Yes, it is about that size.
Thank you.
Yes, I have a question.
Other questions?
According to you, what is the origin of the asymmetry of the pseudogap?
Oh yes, so that depends on the particular model that's used, but all of these models are similar in the sense that if I go back to this plot, they all give you this asymmetric gap, and the reason is, sorry, I'm jumping around a bit. 47 is the slide I want. Whenever you have this reconstruction that takes this form, this can be the YRZ term, or it can be K plus pi pi. You will get this sort of asymmetric gap, even in a charge density wave case also.
Thank you.
Okay. I think we have to stop the discussion and to thank the lecturer again.
Thank you.
And we will continue with the pseudogap pseudo gap between two sessions, and we will fill this pseudo chai gap with a talk by Catherine, which will, and she will try to shorten his talk. Thank you, Catherine, for the improvisation.
So, okay, I'm online. Yeah, I want to thank the team to have reacted so positively to the problem, and thank you for letting me finish the talk. Do I have the access for the? Okay, it seems I'm cursed today. Do I have the access to? Or it's just I didn't. This is total curse. It was switched off, then it's my fault, okay. So I will not take a long time to, but I just wanted to finish, so I like to have things well done. This very nice conference, and not to end up in a state of frustration as I was 1 hour ago. So yeah, it's where I was. So it's a phase diagram. Oh, okay. This is a conversion to PowerPoint. So this beautiful thing is a Carol rotor model. It's not what it should look like, but it's okay. We'll do with that. So it's equivalent to a CP1 model, and the important thing is with this idea of entanglement of charge and spin density, of charge and density wave and superconductivity, you have some chiral model which describing effectively the physics here for those which are field theoretical. And so I have a gauge imaging field here, freezing of all the phase at TC and incoherent boson there. And this has tremendous implications. So first here is the experiment by a group of Seamus-Davis. Here is the charge distribution you see at a finite temperature at B equals 0. And look at the phase slip over there. The distribution of the phase slip is completely random. Now they put 8 Tesla and subtract, and you see the vortex core. And now the distribution of the phase slip inside the vortex core is centered around 0. So it's a completely different distribution from here to there. So it's very difficult to understand because basically the coherence of the phase slip of the charge modulation is 1 order of magnitude bigger, the coherence length, than the coherence on the amplitude of the charge modulation. It is very, very unusual. So within our model, we can explain it by the fact that below TC, it's where they are, the two orders in competitions, they log their phases. Basically, it means that the charge density wave behaves like a pair density wave. I agree it's a bit unusual, but I think if cuprates were so usual, we would have solved them. So, so this as a link, okay, this is a great transparency again. Just to say that with late Konstantin Yefetov, we had work on an idea also where charge and superconductivity are entangled, which this time required an emergent symmetry, not gauge field, but the constraint is the same. And again, it's described by a chiral model below T star. So the two models, it's just different way to get entanglement of charge and particle and particle hole pairs. So I come to the predictions. I will try to go quickly. So we did a bit of RPES. Sorry for equations, guys, but Okay, I'll pass that. So we have a model I will describe with word, which is a TGV model, and we put the strong coupling in a mean field, so it's very kind of lousy with guts filler. And we calculate the particle hole sector and split them a little bit with second nearest neighbor here. So basically what we have as minimal ingredient is the two orders. They have roughly the same order of magnitude, and charge order is a little bit bigger than superconductivity. This is a very minimal model that we could make in order to have a good mean field. And with that, to come to that experiment that James showed you for RPES on bismuth 2212, we can explain it pretty well. Like the constraint is opening the pseudo gap, but the pseudo gap has some structure in Q space, so the KF wave vector are differentiated, and you have the backbanding. So it's one good thing. It's because of the particle that we get the backbanding. So we also compared with the DMFT and the hidden fermion that Professor Imada presented at the last session. And so he claims it doesn't agree, but it's our interpretation that with charge density wave we could identify charge density wave with a hidden fermion. Raman scattering by experiment presented by Alain this morning, we get it naturally. As I said, it was something which was very influential for our work. Just because in order to get this type of emergent gauge field or entanglement, you need to have the two orders at the same order of magnitude, the two gaps, not the two orders, sorry, the two gaps at the same order of magnitude. That's a requirement. So we believe it's important. Also, the charge order gap follows T star and not the charge order temperature, which is something very unique in their experiment. So there is something also charge order, but you see it only below TC, not below TCO, which is something incredible. I mean, why should softening show up below the superconducting temperature? I mean, if it's just two orders in competition, like in niobium diselenite, softening should show up below TCO. And we explain here this with our model by saying that the phase of the two orders lock below TC, but above TC they fluctuate too much and they wash out the softening. I tell you ideas like in one. And then I would like to just say it's maybe the most important. We get some kind of ideas on the strange metal. Again, for people here, the strange metal conundrum was the following. So it's here. It's maybe one of the biggest mystery of cuprates for 30 years. You have linear resistivity for many decades of energy, and when you destroy by irradiation, you see linear resistivity to T equals 0, which is very difficult to get with any model. Moreover, one doesn't see it here, but believe me, it's a quasi-Drude-like. So we know on top of it that if you look at optical conductivity, this linear resistivity is proportional to the Drude width, to the lifetime inferred from the Drude experiment. At the other time, and this was pointed out by Phil Anderson in a very seminal paper, the cotangent hole has a lifetime goes like T square. So if you just do a simple electron model or free carriers model for that, here you have you extract a lifetime which is inversely proportional to T, and here inversely proportional to T squared. So you have two lifetimes. So the way we try to deal with that is tough problem. Here again, another type of experiment, but it goes quick because James mentioned them. This is an experiment by the group of Nigel Hussey in Bristol. And they interpret it, that's discussion with them, as if you have another type of carrier which is present in this region. Okay, they have a new component that they claim is isotropic in the magnetic field, is incoherent, meaning doesn't participate to the thermal hole conductivity, and is participating to this Planckian limit or linear anti-resistivity. So in our model we have incoherent bosons. And one reason also we could get incoherent boson is this wonderful Mills experiment by Mitrano et al. So it's in the strange metal, strange metal here. And you see something incredible. I mean, the compressibility you see as a function of frequency, see this plateau, the energy of this plateau is roughly close to 1 electron volt. It's huge, it's an elephant in the room. So what could cause a plateau at 1 electron volt in this compound? One idea came from people doing statistical physics, actually in my lab, working with actually Parisi, and they told me, oh, but this is a jamming transition. Namely, if we believe them, I don't know, to get a jamming transition, you need to have bosons which interact with each other, and then they jam. Now, why not? We could say that. So we checked in our model, we have bosons which appear at high energy, and they are charged to a finite Q and coupled to the lattice, so they could participate to transport. So we did a first calculation on that. With those bosons. We didn't find literature, any calculation at all, so it's the first one. And we found something very nice. In 2D, they go linear in temperature for resistivity with quasi-Drude-like optical conductivity. And since they are extremely incoherent, they have a Landau damping, you don't see it here, they don't participate to Hall transport. So then the picture would be that they could short-circuit maybe the transport in X direction, longitudinal transport, and then Fermi electrons and Fermi C could be responsible for the T-square in the whole transport. Okay, we also have a prediction, now I pass, in terms of Josephson junction of this very unusual ID, and in particular new Shapiro steps are showing up. So with this, I will thank you for your attention, and thanks to let me present these results.
Okay, thank you, Catherine. Questions? Yes, question from the hall.
Maybe I should talk in the mic. Yes. Well, I have two questions, but maybe we're short of time. But maybe talk about a little bit more about the Shapiro steps. I didn't quite. It was too fast. What is unusual there? Can you explain?
Yeah. So in this work, we try to compare a situation where the two orders compete, and the situation of this fractional sphere density wave where the two orders compete, but the phase lock. So basically, you induce an effective pair density wave. I mean, the charge order. See the phase lock basically in terms of symmetries, your charge order behaves like a pair density wave. And this, when you do a Josephson junction, will induce some tunneling, extra tunneling from the pair density wave sector to the other pair density wave sector. And this produces some observable. So you have extra Shapiro tape, and you have also modulations. If you're able to slide one part compared to the other, you should see modulation at the wave vector of the charge density wave, not half of it. So, I mean, we try to get now some direct experiment, because, I mean, indirect, it was nice, it was very inspirational, but the idea is unusual. I mean, it's an entanglement idea. I mean, around, if you talk to Jansanen or Subir Sachdev, they will tell you that the QCP is the most entangled QCP in the world, and that everything is entangled. So we do something a bit less, bold, but still. So to me, the less bold thing possible is try to entangle the two orders which have been seen with its charge and superconductivity. It's just what we are trying to do.
Okay. Another question? Questions from online? No questions. Let's thanks to the speaker.
Thank you.
And we continue without chai break to the next session. And the chairperson of this session is again Catherine.
Yeah.
Yes.
Oh, we start now?
Yes, because somebody is waiting.
Yeah, sure. Yeah, it's a gapless, pseudo-gap session. So it's a pseudo-gap session, so come online. Vincent Oliviero. Vincent, you are here, I know. Amran, can you go back online? It's not a formula. But I need to check because I saw your talk and I think it has link also with the Dians maybe or. We should sit. Let's sit down at some point. But I'm not so sure the theory is complete. Let's put it this way. We just put this minimal. But maybe it has a biggest theory with emerging gauge field, which has some Dians and stuff. Ah, wait, so. Oh, Vincent, are you around?
Yes, I'm here.
Okay, so Vincent will talk about this high field charge order in underdoped cuprates. Teacher Doreen, can we listen to? You can go for it.
Sorry?
Vincent, you can go for it. The time is yours.
Oh, okay, I just can hear me in the conference room. So maybe can you stop the microphone, something like that? Okay, nice. So I can go?
Yeah. Yes, yes.
Thanks. in Mercury 3 plane, we just perform a Hall effect in a sample around a bit less than 9%, using our 90 Tesla magnet and 70 Tesla magnet. So here I show a sample, the sample. We applied a field parallel to the z-axis. And on the left part, I show the evolution of the Hall coefficient as function of magnetic field for different temperatures. The high temperature, mean temperature higher than 10K, that measurement has been done in our 70 Tesla magnet. But for the lower temperature, the very high critical field because of the very high critical field, we used our 90 Tesla magnet to reach the normal state, and this is why the data are a bit more noisy because of the high dB in the 90 Tesla magnet. But in any case, what we can clearly see here is the fact that in the normal state, the Hall coefficient remains positive whatever the temperature. And we can plot from the value of Hall coefficient in the normal state, the evolution of this Hall coefficient as function of temperature. And we just here show that it remains positive even at 4.2K, which strongly contrasts with the case of Mercury 1 plane, where the Hall coefficient just dropped due to the charge order and become negative. So here, what I did, I just summarized our data. First for Mercury 3 plane, where we measure 3 main frequencies and a simple relation between those frequencies. We compare it to Mercury 1 plane, so one frequency is same, the F3, but the large difference, the huge difference, is the positive Hall effect in Mercury 3 plane and the negative Hall effect in Mercury 1 plane. So now the goal is to reconcile our data and to try to draw a Fermi surface of our compound. So in this first scenario, so I will propose 2 scenarios. And the first scenario is just a scenario where we thought about another compound with several layers per unit cell, and here it's YBCO. In YBCO, it's well known that charge order also developed in the order region, but the spectrum of the quantum oscillation is not composed of only one frequency. It's composed of a central frequency and 2 satellites. And satellites are due to the coupling between layers, which lead to the observation of other frequencies, and it's well understood in this paper or in other papers like the Maharaja paper. And what we can assume is the fact that in Mercury 3 plane, we got also charge order, which correspond to the 850 Tesla frequency in analogy to Mercury 1 plane. But that tunneling occurs between layers, so jump term is present, and lead to the observation of additional frequencies in our spectrum in analogy to YBCO, to the YBCO system. And the main difficulty and problem with this model is that, of course, the Hall effect should be negative in this model because carriers are electrons. But also, we expect to observe a symmetric spectrum like in YBCO with main frequency corresponding to the electron pocket and satellites around this frequency. So the model of just tunneling and charge order cannot explain the negative Hall effect, and we have to find another way to explain our data. So this leads to the second scenario, where here we just took into account the characteristic of multilayer. And the main characteristic is the doping imbalance between layers, as I present in the first part of this talk. And what we can assume is we have doping imbalance in Mercury 3 plane, which is very general, and that the inner plane is less doped and is in an antiferromagnetic order. In this situation, what you expect to observe is a frequency in your quantum oscillation spectrum around 500 Tesla, which corresponds to peak areas, And this is just here. So the high frequency measure here corresponds to the frequency F2. On the other hand, we can also think about the fact that the outer planes are slightly more doped than inner planes. So they are outside the antiferromagnetic order, but present in a charge order phase. And charge order, I remind you, has been measured by Raman spectroscopy. And in this situation, in analogy with mercury 1 plane, what you expect to measure is a frequency around 850 Tesla, which is our frequency F3. And now we can also think to the scenario of YBCO, where tunneling occurs between planes, leading to the observation of the frequency F3, which is equal to the difference of the two frequencies, because we are tunneling between an electron pocket and an hole pocket. But what about the Hall effect in this situation? In this situation, what you expect how you expect to analyze your data is to analyze the Hall effect in a two-band model. And in a two-band model, the Hall effect just depends on the mobility ratio between carriers. In our situation, we expect to have an higher mobility in the inner plane because it's cleaner than outer plane. And a positive Hall effect for Mercury 3 plane corresponds to a carrier mobility ratio of 3. So inner plane mobility is 3 times larger than outer plane. And this number is coherent with other measurements. Like, for example, when I present the data with a 5-layer compound, they just measure a ratio of mobility of 2 between the two inner planes. So in our situation, we are dominated by the hole in the inner plane in terms of transport. This is the reason why we measure a positive Hall coefficient. So here I just summarize our model. We are studying a Mercury 3 plane compound, which is a multi-layer. There is a doping unbalance, making the inner planes in an antiferromagnetic order. And this antiferromagnetic order, the whole pocket of the antiferromagnetic order, just dominates the transport, leading to the observation of a positive Hall coefficient. But outer planes are slightly more doped. So we observe 850 Tesla frequency, which corresponds to the electron pocket. So we can understand those two frequencies, and by tunneling between layers, we observe also a frequency F1, which corresponds to the jump between the three layers. So I was a bit fast, but I would like now to conclude maybe, and to just first say that we measure for the first time quantum oscillation in the Mercury 3 plane, which is a compound with a higher TC at ambient pressure among all cuprates. And by completing our measurement with Hall effect, we could analyze them as a coexistence of antiferromagnetism in the inner plane and charge order in the outer plane. So I draw here just phase diagram, sketch of the phase diagram of Mercury 3 plane. And this is very interesting because the coexistence of charge order of antiferromagnetism and superconductivity, as I told you, is general feature of multi-layer, but also what has been measured by resonant X-ray scattering in the Mercury 1 plane and Mercury 2 plane, and also other cuprates, is the fact that the magnetic action strength just match the higher TC of the compound, the TC at optimal doping of those compounds. So this shows a very important link between magnetism, antiferromagnetism, magnetic exchange, and superconductivity. But in another hand, we also have a strong link, as shown by Raman spectroscopy, for example, where the charge order gap, the doping dependence of the charge order gap just match the gap of the superconductivity in Mercury 3 plane. So the fact that we can observe both charge order and antiferromagnetism coexisting in a 3-layer in the cuprate with a higher TC is very exciting, and maybe we'll be able to measure other samples, and that's it. And I would like to thank you for your attention, and I'm open for any questions.
Thank you. There are questions for Vincent? Okay, let me start the discussion with you, Vincent. So you showed beautifully on these 3 layers that I think it's very convincing analysis that the intermediate layer is is a charge order, and on no, it's the opposite. And, on the top is charge order, yeah, and intermediate layer is antiferromagnetic. So in that case, it's beautiful school case almost that we see all the pockets. We see whole pocket for antiferromagnetism, electron pocket for charge order, and we even see the frequency between the two. So I come back to the question that was asked to James Story a bit earlier. The fact that we see only one frequency when there is no explicit antiferromagnetism, does it show that there is no whole pocket due to the mode transition, but it's only due to antiferromagnetism, the whole pocket? I mean, it's a bit maybe provocative question for you. Is it? It's the only case. Yeah.
You are talking about the inner plane, yes?
Yeah, yeah. So if there was no antiferromagnetism, you would not see the pocket. Let's put it this way.
If there is no antiferromagnetism, in my case, as I understood, if there is no antiferromagnetism, it's just like Fermi arc, you expect to see a local oscillation. I'm not sure if I answered to the question.
Well, there are theories who say that you can have whole pockets without antiferromagnetism. That's one thing. I mean, generic theories that you dope a whole mode insulator with you form the whole pockets if you just do a simple theoretical analysis. So and they are not exactly centered in the antiferromagnetic zone. They are just a bit pushed away. So this you have never observed, you confirm?
By quantum oscillation, I confirm just the way we understand our data. Of course, we just compare to other data in the sense that, as I know, quantum oscillation just measures the whole pocket to antiferromagnetism. If it's due to other confirmed or other model, I'm sorry, I can't really answer this question. I just know that this pocket corresponds to peak areas. And I don't know, maybe in other models we also observe peak areas. I don't know if my question is relevant. Do you expect to see peak areas?
To see what, sorry? To see what?
An area corresponding to peak areas in the other models.
To P, sorry, say in French. It's just your English and my English. To peak,
I'm sorry, it's my English. Yes, because this pocket, this pocket corresponds to the doping value, like the number of folds per pocket.
Yeah, yeah.
The area of this pocket.
Yeah.
And in other models, do you expect to see the same area?
Yes, yes. If you just do a strong coupling model for mode insulator, you create pockets which have the surface of the hole. That's.
Okay, so we just have access to the area, so I'm not sure we are able to make the distinction between one model and the other one. Yeah.
Okay. Do you have another probe to know that it's antiferromagnetism for this special compound, the layer in between? It's just quantum oscillation with a frequency, or is it? Do you have another probe? Like I don't know which probe. It's in the inner plane, so NMR will not work.
This compound, but from the other families, the ARPES data shows the presence of the whole pocket in the nodal region. So I come back. Yes, just here.
Yeah.
So it's not the same compound, it's also a multi-layer, and they show the presence of the
So
yeah.
So here we know it's antiferromagnetic because it's zone boundary. Yeah. Sorry.
And
yeah.
They also, from this experiment, they also observe the superconducting gap in the inner plane, in the inner plane Y, so directly in the ARPES data.
There is another question for you, Vincent.
Do you hear me?
Yeah, I can hear. Yeah.
Why do you have this ratio that F1 equals F3 minus F2?
The reason is because of, in our model, we explain this frequency by the tunneling between the two planes. So in a quantum oscillation, where you are tunneling between two planes, two pockets of different areas, you expect to see the sum of those pockets, but if pockets are not in the same carrier, here it's electron and this one, we expect to see the difference. So that's how we understand this frequency at 3. Frequency at 1, sorry, is equal to the difference of the electron in the pocket.
Is there other question for one? Yeah.
Yes, I have a question. Could you explain why the charge density wave developed preferentially in the outer plane and not in the inner plane?
In this, like here, we just assume it's due to a doping imbalance. So I did something just here. So maybe you can help me to explain that here what I show is measurement of doping of inner plane and outer plane. So by NMR, they are able to estimate the doping in inner plane and outer plane of this three-plane compound, which is close structurally geometric. And this allows us to have an idea of the doping imbalance between layers. And I took here the mercury one-plane phase diagram, the mercury one-plane, and I just show by this line the doping imbalance between inner plane and outer plane. So how we understand our data is like that you can see it's not just few percent, it's large. So we understand that outer planes developed here are just more up, and in the phase diagram, like in mercury one-plane, the charge order developed at some doping value, critical doping value. Yes, so we just assume the inner plane are less, the outer plane are more up, so in a charge order.
That's very useful.
Absolutely.
But my point is why charge density wave developed preferentially in the outer plane. That's just the scenario that you propose, but how do you justify this point?
We justify this point just because it will also explain our data. And the preferentially, it's not like it choose to be in one plane and not in another. We just explain it by a doping imbalance. But I don't know, I cannot answer really if there are some reasons why charge order develop really preferentially in outer planes and inner plane. Maybe it can be due to disorder, but I'm not very clear with that. So,
can I do something?
Yeah, of course.
So I mean, looking at the Bisco and Mercury, it seems to me that if antiferromagnetism is strong, then you get a hole pocket. The antiferromagnetism is not strong, but charge density wave is strong, you get electron pocket. But when neither is strong, you will remain with arc. And you know, this Bisco data is really beautiful because they show arc pocket on the same compound. So arcs are not pure imagination.
So I think
That also answers that. That's a question. More like a comment.
thank you, Niven, for your comment. I think it does, indeed. Shall we thank the speaker again? And now we welcome Theodore Michonov, and he will talk to us about cold spots and hot spots in the Fermi surface of those compounds.
Okay. We're having a technical problem. Just 1 minute, please. I can speak with. This is the pointer. Oh yes, and this is next slide. And forward and next. Okay. This next step is we'll just have to yes, we need to because we have the same problem. We have a PPT version, PowerPoint version of the file.
So, is it working on the technical? Okay. Here it is.
Okay. First of all, I wish to present my co-authors. Nedelcu is in Sofia, but Albert Baronov is here, somewhere here, in the hall. So I wish to focus your attention about the common picture of hot and cold spots in thermic contour. I have no three hands, so we will use this one. Thank you very much. Because we are staying on the position of fundamentalism, and we wish with one and the same Hamiltonian to describe superconducting properties of the overdoped and optimally doped superconductors, and simultaneously the normal state properties. Hot and cold spots, they was invented 20 years ago as a phenomenology, but now we are happy to derive this phenomenology from the microscopic Hamiltonian. So those are ARPES data for so-called hot spots along the Fermi contour. And we are trying to explain how those hot spots emerged from the standard model of pairing mechanism. What is the standard model of cuprate plane? We have 4 different orbitals, oxygen orbitals, very important 3D orbital, and from time to time people introduce copper 4s orbital, which is extremely important from our point of view. We are using linear combination of atomic orbitals, and T means transfer between different orbitals. Linear combination of atomic orbital is the basis of the chemical intuition, and we will apply this chemical intuition into the physics of superconductivity. Sorry for this incompatibility of the equation of the computers, but I will skip that. Wave function is linear combination of wave functions of different orbitals, and we have single particle orbital, which is starting point of statistical considerations. So in the picture we can see not only Hoping integrals, which are very famous, but also Kondo exchange two-electron interaction. This two-electron interaction is actually correlation. One s electron becomes d electron, and simultaneously one d electron becomes s electron. This is so-called SD, or Kondo interaction, and the name of Kondo I have listened in this conference at least 4 times. So we included in Hamiltonian Kondo interaction as an exchange pairing mechanism. Let me see some formula where something can be seen. So so from this exchange interaction, this is a cartoon for exchange interaction, Kondo exchange interaction. Imagine what is S electron. S electron is like a kamikaze electron which is falling to the nucleus and resurrecting then, and the electron is rotating in a circular orbit. But 2 electrons can change his orbitals, and this is SD exchange mechanism. There is already a book systematizing those technical details. I will skip all those technical details which are standard, but we are presenting those orbital, those calculations. Formulas cannot be read in this representation. So, if we have standard BCS reduction made actually by Bogolyubov, we derive some BCS pairing kernel which is factorized by a function from different wave vectors. And running ahead to my presentation, I will say that the same kernel arises again from the Fermi liquid reduction of the same Hamiltonian. I will skip unreadable details. Actually, I have a PDF of our calculation. We have an abridged version. Everybody asking I can give you my unabridged version of the PDF. So this is the standard band structure, which is repeated by a lot of local density approximation, and this is atomic wave interpolation of the well-known electron band structure. We have a conduction D band and Fermi level crossing this D band. So in our kernel, we obtained analytical solution for the factorization, and gap anisotropy is proportional to two well-calculated functions. This is hybridization function, which has a saddle point shape, and this saddle point is crucial for the understanding of cuprate gap anisotropy and hot and cold spots. This is velocity calculated from the band structure, which is standard. In BCS theory, we have tangens hyperbolicus integrand, which can be drawn for this rounded square shape of the Fermi surface. And what we can see is those are data by Campuzano. We have a Fermi surface. We have D-type gap anisotropy, and those experimental data are RPS data for by Campuzano for the energy gap of optimally docked cuprate. We have integrand for BCS theory, but BCS theory and pairing is just starting point of our consideration, because I consider that pairing is slightly trivial, much more rich for effect is the normal phase. What is the most remarkable observation in electron band calculations? This is Pavarini Anderson correlation between the shape of Fermi contour and critical temperature. We know that practically all phase transitions are created by some interaction. But how is possible shape of the Fermi surface, which is a property of non-interacting electrons, to correlate so perfectly with the critical temperature? Because Pavarini and Anderson takes some points in the diagonal and these points, and from those points they calculate some dimensionless parameter which perfectly describe a correlation between the shape of Fermi contour and critical temperature. No explanation. This paper has about 200 citations, but no one of those citation is related to some microscopic explanation. Moreover, it is achievement by Albert. He put the red crosses. Red crosses are experiment. ARPE's experiment together with electron band calculations, two absolutely different methods, gives one and the same methods. And the continuous line is our initial theory. Theory is not so good, but there is no better theory at the moment. This is a BCS treatment of the Kondo exchange interaction, which describes this correlation. Now I am trying to present the Landau-Fermi liquid reduction of, and self-consistent approximation. And again, if we apply the Landau theory of Fermi liquids, we again from the same Kondo Hamiltonian obtain the same factorizable kernel, which is very important for the Fermi theory. And no, I put in archive, but it is blocked already 2 weeks. Archive now is not working. 3 weeks ago we put in archive, but still is not accessible. So I cannot make better solution, but I have to make a pantomima. So we have conductor which has layers. We have parallel layers. Between those layers, we have vacuum. We have electric field which can fluctuate between those layers. Who could be flying for the blue sky? We have electric field between layers, and this is like a plane capacitor. In every plane capacitor, we have charging energy, which is determined by the thermal fluctuations. And we are obliged to take into account the thermal fluctuations. Thermal fluctuations cannot be forgotten. They have to be taken into account. But fluctuations of electric field is related to fluctuations of density. Fluctuations of density is something very important. Fluctuations of density is related to as a scattering mechanism. We are taking microscopic Hamiltonian, which pairing, and put this Hamiltonian in old theory of Lord Rayleigh for scattering of waves by density fluctuations. And we succeed to describe the this phenomenology of hot and spot regions. Those are our calculations. I mean, colors describe intensity of scattering, single particle scattering along the Fermi contour. So at those places where experimentalists by ARPES observe hot spots, we calculate strong scattering of charged particles. So this is our function which analytically describes scattering rate. This is Kondo scattering rate, two-channel scattering rate by Kondo interaction, and we have hot spots. And also we can calculate phenomenology of Drude conductivity. Drude conductivity is parameterized by some effective scattering time, but this scattering time has to be integrated. And in spite of the poor quality of the written, we can explain our final result by pictures. This is theoretical picture for Fermi contour and our hot spots. Those are ARPES data for which provoke us to start these calculations. And in this view graph, Albert put our calculations on the ARPES data, and this is theory over experiment. So what is the final message of our presentation? One and the same microscopic Hamiltonian as the microscopic Hamiltonian can describe phenomenology of anisotropy, strong anisotropy of scattering of normal charge carriers, and simultaneously pairing anisotropy of cuprates. This is, I think, a good beginning, and theory is not very precise, but this is like a submarine which can fly or airplane which can dive. We can go in different area. I think that's it, full stop.
So let's thank Todor for this very nice talk in a bit tough conditions with the equations, but I think we could follow the ideas. So is there questions for Todor, or shall I start the discussion? No, let me start then the discussion. So it's very interesting if, I mean, from a microscopic model, you can predict there is hot spots and cold spots. You know that in a less microscopic model, like theories of spin fermions, you could have hot and cold spin, for example, from antiferromagnetic fluctuations or from charge ordering. How do you make the link with antiferromagnetism or charge ordering? Can you get them from your microscopic model? Do you think your Kondo interaction? Formula came back.
Yes, I think this approach is very flexible and can be applied in many different.
We missed to work with good formulas. I mean, it's like.
But with imagination and strength of the
mind, yeah.
The mind, you compensated this. So this, what is necessary? It's necessary to calculate electron band structures from LKO model. This is already matrix 4x4 or 6x6.
But can you predict that it will give antiferromagnetism or charge ordering from this Kondo interaction? Can you predict that it will be give one of the two to to be coherent with the kind of phenomenological description we have?
I think yes, it is matter of time of manpower. I think it is possible the same approach to be applied in a lot of systems in which exchange interaction dominates.
So then it will be very interesting to see if it produces charge ordering, what is the wave vector it gets.
Yes, yes.
Because those wave vectors are very notoriously difficult to get from any microscopic model, and the one observed by X-rays and Fermi surface reconstruction. So it would be very nice to see whether you can get them.
Why I'm here.
Okay.
Searching for people thinking in this direction, and I forgot to congratulate organizers for such good running conference after this delay. This is a big success. Again, our biofield to be fixed on the superconductivity and magnetism.
Okay, this is true. I agree. So let's congratulate Ali who is in the room.
Yeah.
So more question for Todor.
Question second time. No questions third time.
It's your last chance. So if not, let's move to the next speaker. Let's thank Todor again. So the next speaker is Isabella, and she will talk to us about the new interpretation of the anomalous dispersion relation for neodymium, cerium, copper.
Thank you very much for an introduction. So now we will come back to the topic of charge density wave and electron-phonon interaction that can be possibly caused by this kind of ordering. So at the beginning, I would like to mention my collaborators, theoreticians from Polish Academy of Sciences in Kraków, Professor Piekarz, Ptok and Kapcia, and our collaborators from University of Minnesota, who provides us perfect single crystals. And I would like to also thank the National Agency for Academics Exchange in Poland, who enabled me to be here and present you these studies. So let's start with charge density wave order. It's a charge order which coexists with superconductivity within copper-oxygen planes. It is incommensurate charge order, quite well defined. For example, we define temperature and doping dependence of this charge order for a simple mercury 1-201. It was observed in many cuprates, so it's like quite well-known phenomena. It appears within the underdoped part of cuprate's phase diagram, within the pseudo-gap phase, and it can strongly affect the electronic structure of cuprates. It can, for example, reconstruct the Fermi surface of the material in a big hole-like to the Fermi liquid-like to the small electron pockets within this violet area under high magnetic fields. But charge density wave order not only coexist with superconductivity, it also competes with superconductivity. It can be seen on this picture when the intensity of the charge order is shown as a function of external magnetic field. This intensity is growing, while at the same time superconductivity is of course suppressed. So these two phenomena are competitive to each other. However, we don't know clearly the mechanism of this competition, and that's quite interesting. That's why we are still investigate charge density wave order highly. So charge density wave order, it was can also affect lattice dynamics of the material, and it was shown in 2013 that the charge density wave order around the Q vector of charge density wave order, some anomalous softening of acoustic phonon modes appears. It was shown for yttrium, barium, copper oxide. And this softening, as it was said on Catherine's presentation, the softening is reported below TC at and also within the doping range where the superconductivity occurs. However, it was also shown that the electron phonon coupling in this case it's not strong enough to cause appearance of superconductivity of pairing. So we knew that the charge density wave order is not responsible itself for superconductivity. However, it was quite interesting, and people tried to explore the influence of charge density wave order on phonons more highly. And that's the point where it was also shown that the charge density wave order can cause softening of high energy optic phonon modes, and that was shown for a striped system, lanthanum barium copper oxide, and here we see this softening around QCDW. Also, more recent data are showing similar results, and that's data, that's RIX studies performed by Johan Chang's group, and it was also done for striped system, lanthanum europium copper oxide, and also around QCDW, a softening of high energy phonon mode was shown. However, RIG studies are limited because of their resolution. The resolution is in the range tens of millielectronvolts. We know better, maybe not better, but different techniques that can also explore phonons more carefully. And that's why here I'm showing results for from inelastic X-ray scattering technique and anomalous softening of high energy optic phonon mode for neodymium cerium copper oxide. It was reported nearly 20 years ago. Here it is signed by this green circle, and now I explain what it means. It means that this green high energy phonon mode softens around Q equals 0.2, while the second mode, the blue one, stays at the same energy. And it was reported for Q equals 0.2, similar wave vector at which also QCDW was reported at 2015. So the question was, is it also true for not only for a striped system, but like for a very simple cuprate, that the phonon softening can appear because of the presence of charge density wave order? Is it a generic property of all cuprates? Is it like a generic electron phonon coupling? And this motivates us to perform our studies. So what we did was to redo this experiment and make it in for different temperatures and dopings also for the same compound, neodymium cerium copper oxide. Why for this compound? Because it's a very simple one with one copper oxygen plane per unit cell, and also another advantage is that for this compound charge order appears at very wide range of temperatures and dopings. So it's quite easy to follow charge order in this compound. So our approach was to choose two different samples, two different dopings, underdoped sample and optimally doped sample. Why? Because for optimally doped sample, charge density wave peak seen by resonant X-ray scattering, so quite standard method to explore charge order in cuprates. So this peak, charge density wave peak for optimally doped sample is very prominent here. Its intensity is decreasing with temperature, but saturates around 300 Ks. However, the situation is different for underdoped samples, because here the charge order peak is not visible, so we have only a background visible here and a little bit of this peak at low temperatures. So yeah, we have two different regions for charge density wave order, and our approach was to compare the evolution of phonon dispersion for these two different samples. We also explored different temperatures because we see that charge density wave order is highly temperature dependent phenomena. And to do that, we went to ESRF, beamline ID28, and that's the schematic of this beamline. But what is the most important for us is the resolution that this beamline can give us. It's about 3 millielectron volts, so we can really differentiate between different phonon modes. That's quite important for us, especially if we want to compare to the older data with lower resolution. And we explored phonon dispersion along copper-oxygen planes and copper-oxygen chains along this direction with transfer momentum as the one mentioned here. And that's example of our results. Results for optimally doped sample at 300 Ks. This part is a part of acoustic phonon modes, and the middle panel is for optical phonon modes. And here we also have the green and the blue mode. The green mode is shifting in energy towards lower energies, while the blue mode is shifting to higher energies, going up with Q vector. So it means that these two modes cross at point around 0.2. They overlap at this point. And in our interpretation, there is no anomalous softening of the green modes, just crossing of them around 0.2, crossing or anti-crossing. So that's what we propose for this dispersion relation. And the dispersion relation is plotted here on the top of DFT data, because to be sure that our interpretation is okay, we performed calculations. And that's data for optimally doped sample. As you can see, the data follows nicely calculations, except of these two highest phonon branches, so the one for which the anomalous softening was reported. Calculations marked on this picture by gray lines are calculations for parent compounds, so antiferromagnetic one. And that was our first thought, that maybe that's the reason why these two branches doesn't correspond nicely to the calculations. And what we did, we changed a little bit our approach for calculations. We set U equals 0, J equals 0, and calculated once again. And at this case, for parent compound, what we get was two anti-crossing phonon modes. They have the same symmetry and anti-cross about a point of x equals 0.2. And that's exactly what is going on in our case. We also calculated dynamic structure factor for inelastic X-ray scattering studies, and the intensities that we got agrees very well with the intensity of phonon modes we measured. And what I can see more about this vibration of phonon atoms that we can observe here for these two branches is that the blue branch corresponds to the vibrations of all oxygen atoms, while the green mode corresponds to the vibrations of only oxygen atoms within copper-oxygen planes. So these are bond stretching modes. So we see that only oxygen atoms are involved in the vibrations which are drastically changed between undoped and doped material. That's kind of important information. Now I'm adding to the previous picture, I'm adding points for underdoped sample. And as you can see, they are at pretty similar places. So these two data sets are very similar within experimental error. So they can be named as a complementary. So the conclusion is we don't see any doping dependence. And at the beginning I've said that the charge density wave order phenomena is really doping dependent. So what I'm saying is that there is no influence of charge density wave order on the dispersion of phonon modes along copper-oxygen planes. And that's kind of important. But on the other hand, what we can say is that this anomalous anti-crossing is not really anomalous, it's just internal property of the material. And to prove that, we also performed temperature-dependent studies. And so we go through these points across the phase diagram of NCCO. So we compared inelastic X-ray scattering data for different temperatures and at different wave vectors, close to the CDW wave vector and also at other points. And what we see is that observed phonons are exactly at the same energy, at the same position. The only thing that is changing is the contribution from elastic lines, so the whole spectrum is going up here. But we, again, we don't see any influence of temperature on the dispersion relation, while the charge density wave is clearly temperature-dependent phenomena. So, again, charge density wave doesn't change phonon dispersion that we probed. However, we've seen some anomalous behavior. And here you have, once again, the blue mode and the green mode, but for different temperatures. And we've seen an anomalous broadening of this blue mode. And that's the picture in the middle. So it's temperature-independent broadening. And then we went back to the publications of Resnick from 2006. And what they are saying is that they predict that some dynamic charge in homogeneities can cause this kind of behavior, so broadening of phonon modes. And actually, dynamic charge fluctuations, dynamic charge density wave was seen in neodymium cerium copper oxide. It was published in 2016. And this kind of feature is visible and is temperature independent. And what is more, it's also coupled to paramagnon dispersion. So at the same time, this charge density wave, dynamic charge density wave and paramagnon contribution are increasing at resonant inelastic X-ray scattering spectra. And that's shown on these two pictures. And my message is that we are saying that this kind of dynamic fluctuations are causing anomalous behavior of phonon modes about the wave vector, of course, of these dynamic fluctuations. And we also, this phenomena of these dynamic fluctuations is generic property of cuprates. We measure that also for whole-doped mercury 1-201. So to summarize my presentation, I've presented a new interpretation of the dispersion relation for model electron-doped cuprate NCCO, and our interpretation agrees quite well with DFT calculations. I'm also saying that the static charge density wave order does not influence the dispersion of phonon modes. There is no temperature nor doping dependence that is characteristic for a charge density wave order. I'm also saying that this anomalous softening of bond stretching mode is not generic property of all cuprates. It was observed for striped order systems, but it wasn't observed for any other system where the stripe are not present. And we see in our studies some indication of electron-phonon coupling that possibly is caused by dynamic charge density wave order coupled with paramagnons. And with that, I would like to thank you for your attention.
So, are there questions? So I can start again.